Hello, everyone, and welcome back. In this lecture, we're going to continue our discussion of Riemann sums. We're going to formalize this by discussing definite integrals. So let's go ahead and get started. Okay, so let's remind ourselves what we were talking about in the previous lecture. We were given a function, f of x, and it was said to be on an interval a to b. And we saw that we can construct a Riemann sum in the following way. We first saw that we can define a spatial step size that evenly partitions the interval AB into exactly n subintervals. So that is the length of the interval b minus a divided by the number of subintervals n. And we can define the points that make up the endpoints of these subintervals by saying x0 is the leftmost interval, the leftmost element of the interval. So if we want to see what this looks like on a number line, we have x0, which is a, and then x1, which is the next term up. This is a distance of delta x in here. So this is a plus delta x. So x1 is equal to a plus delta x, the right endpoint of the first subinterval. And then the next term is another delta x jump forward. So my picture's already getting crowded here, so I'm going to refrain from writing this. I'll write it below, but I get, I get x1 plus delta x. And I can use the formula for x1 above to see that this is no more than a plus 2 delta x, 2 intervals away from where you started. And you can repeat this process to get general xk is equal to a plus k delta x. It is k subintervals away from where you started. Okay, so then on each one of those subintervals, we take an intermediate point. So take ck in the subinterval xk to xk plus 1. And we can define the Riemann sum. So the Riemann sum is given by summing over all of these rectangles whose base is given by the subinterval or the length of the subinterval, and whose height is given by the value of the function at the ck's. So the area of each one of these rectangles is height times base. Now, what we saw with the example from the previous lecture of 1 minus x squared was that this gave a general formula in terms of n when we worked it out. And we saw that we can take the limit as n goes to infinity in this case. Now, let's imagine we can do that again, just for simplicity. Let's imagine this limit exists, okay? So the way you approach this is exactly how we did it in the last lecture. You're given a function, you need to work out this sum in terms of general n, and then you ask yourself, can I take the limit as n goes to infinity? We're going to classify the functions that this actually works for in a moment, but let's imagine this works. Well, we have a mathematical shorthand to denote the answer here. So this will be a single number, right? We're summing up just a bunch of areas of rectangles. And so the mathematical shorthand is given by this curvy S looking thing, which is an integral operator. So the reason it looks like an S is because it's supposed to be a script S representing a sum. Okay, so it's not as clever maybe, or it's kind of clever. And we're going to put the left and right bounds at the bottom and top respectively of this big S. So just like with my sum notation here, it starts at the left and goes to the right. Well, I have the same thing, but if you think about what's happening as the limit as n goes to infinity, you have infinitely many sub-intervals now. So this you can think of as an infinite sum operator, right? It starts at A and it moves infinitesimally forward to get to B. This is a sort of loose way of thinking about this, but that means that your delta x now becomes, we write it as dx. This is infinitesimal notation. You might be familiar with this from Leibniz notation as well. This is just change in x in an infinitesimal manner. And that is the base. That's the length of each one of these subintervals in an abstract manner. And so for each value of x, the height of these rectangles is given by f of x. So this is a very, very abstract way of this sum where these left and right endpoints are converging onto each other. And that's coming from the fact that delta x is going to 0, right? So the size of each one of these intervals, you're getting more and more packed into the interval from A to B, but each one takes up less and less space. So this is just a very, very abstract way to quantify this limiting sum. So what happens as the number of sub-intervals goes to infinity? I don't want you to get hung up on notation here. This is just a number. Don't get excited about it. Don't get intimidated by it. This is just a number. And it's just our short form in mathematics for saying what this number should be, right? There's, all the information is encoded there. What is the function I'm interested in? Where does it start and where does it end? It's just, all it is this right-hand side written compactly. I don't have to write the limit anymore. So this sort of begs the question, right? What the heck functions can I actually take? You know, when does this limit even exist? When can I take an integral of these functions? When do I know that the right-hand side actually is a number and not like infinity or something like that just doesn't make any interpretable sense? Well, luckily for us in this class, pretty much everything that we're going to see is actually going to be able to be put into this integral. But let's actually say, you know, let me give you a theorem that tells you which functions I'm allowed to put into this Riemann sum and know that that limit exists. So if a function f is continuous on AB, or if f has finitely many jump discontinuities, then this is called a definite integral. This definite integral exists. Definite integral exists. You know, and so just in case we're following along at home, this thing is the definite integral. Okay. So let's think about this sort of informally, right? What does it mean to be what does it mean to be continuous? Well, typically the loose definition that we're given for continuity of a function is that, you can draw it without lifting your pencil. That is a very apt way of characterizing continuity for these one-dimensional functions we're going to be interested in. And so what does this little theorem say? This result that tells us which ones I can take the integral of and which ones we should be working with. Well, it says it's either got to be continuous or it has finitely many jump discontinuities. So what's the informal way of saying this? Well, to draw the function, I only have to lift my pencil finitely many times. That's how you should be thinking about this. And we're not going to prove this. It's sort of outside the scope of what I want to do in this video, but the proof is actually quite easy. And the way that you do this is you work with the original Riemann sum, and you choose CK to be the value of x that either gives the maximum over each interval or the minimum over each interval. And just like we saw in the previous video, that means that you're sort of overestimating and underestimating this sum. And you can show that these things will converge for this and lead to this definite integral. So the question is, why do you need continuity, or why do you need finitely many discontinuities to do this? Well, the answer is that you need to be able to find a maximum and a minimum. So these are the types of functions where maximums and minimums are well defined. So, let's have a bit of fun though, right? This is a math class. We delve in the abstract. We think about possibilities where things can go wrong. So let me give you an example of a function this doesn't work for. Okay. This function is very famous in mathematics because it leads to all kinds of problems. So here is a very ugly function. This function is going to be 1 if x is rational, right? So rational means it can be written as the quotient, the fraction of two integers. And it's going to be 0 if x is irrational, right? So this is 1. It's going to take on 1 if it's rational, repeating decimal places, or at least a pattern to the decimals. 0 if it's irrational, sort of like pi and e and most numbers, right? So, okay, so what do we know? I'm just going to talk this one out. We're not going to go through it all. But what do we know about this thing? First of all, in any interval, you give me any interval that has a non-trivial width, so some delta x, I can always find a rational number in there, and I can always find an irrational number in there. So if you think about what I just said for how you would prove the theorem that I just showed you, your upper approximation, so upper, is going to be the limit as n goes to infinity. Actually, let's take the limit out for now. Let's just do a finite Riemann sum. This will be the sum from k equal to 1 to n. And you want to take the maximum on every single interval. Well, every single interval contains a rational number. So the maximum on every interval is 1. And then you multiply this by delta x. And I forgot to mention this. We're going to put this on 0, 1. You can do it on any finite interval you want, minus a million to plus a trillion. Doesn't matter, right? You're always going to see that this isn't going to work. But I should be specific about this, right? And so what do I get here? My delta x is 1 over n. So I get, the sum of k equal to 1 to n of 1 over n. So this is equal to 1. Okay, that's not bad, right? So no matter what the value of n you choose is, you are going to get the upper approximation for this thing to be 1. Okay, so what's the lower approximation, right? You can probably see where this is going. Well, the lower approximation is given by the minimum over each interval. And every single interval contains an irrational number. And so that means that I'm going to get 0 is the minimum on here times delta x. Okay, so here's the issue, right? I have a lower approximation that is 0, that's independent of n. So I take a limit there, it's still 0. I have an upper approximation that is 1, it's independent of n as well. I take a limit, it's still 1. These things are not the same, right? So what happens? Well, if you think about how the Riemann sum is defined, it doesn't matter what CK is. Remember, if you think back to the previous video, I said you can choose CK to be whatever you want, right? You can make your life really miserable and choose these really complicated ways of finding it, or you can make it really simple and use like the left or right endpoints. But it shouldn't matter for a Riemann sum to actually exist, to be able to apply this theorem. But here, I showed you that it matters, right? Because these things do not converge to each other. And therefore, you know, the definite integral does not exist. So therefore, the integral from 0 to 1 of f of x dx does not exist. So this is sort of like a classic example in calculus and integrable functions of something that is just truly, truly horrible and does not work, right? And you know, sometimes I just sit around and think about what this function looks like, and it just makes me dizzy, right? I urge you to try and visualize this function. It's just a ridiculously complicated function, and luckily for all of us, you know, we're not going to have to worry about that function because we're worried about functions that we can take definite integrals of. Okay, so we have the idea of definite integrals. We know that certain definite integrals exist, right? And in particular, that's functions with finitely many discontinuities. 0 is a finite number, so we'll say finitely many discontinuities. Okay, so the question is, you know, what are sort of some of the properties of these definite integrals? So, right, one of the best things that we do in math is come up with a bunch of properties to save us work. I don't want to have to rederive all of this, like this sort of cumbersome stuff over and over and over again. What I want to be able to do is I want to have like a list of properties that I can just draw upon and say, oh yeah, okay, I don't have to recompute all of this stuff. It's just that one that I saw previously, and then I tweak it a little bit with some properties. Okay, so let me give you the first one. The order of integration. So if I give you a definite integral from a to b of f of x dx, this is the same as the negative of the definite integral from b to a of f of x dx. Okay, so what the heck is going on here, right? Well, think of the left-hand side, what's happening. So if a is smaller than b, your interval runs from a to b. And so then your delta x is positive, right? B minus a divided by n, you're increasing by delta x each time. Then we let delta x go to 0, and we get this sort of abstract, summation, this super continuous sort of abstract summation. Okay, then think about it the other way. Let's look at the right-hand side here. Right, so I'm running from B to A. B is bigger. That means that I'm running from right to left. My delta x is negative in this case. So that negative of the delta x eventually becomes this thing, my infinitesimal, and the negative stays with it. So that negative gets stuck outside. So this is just saying, this is just telling you that direction matters, right? It's just like how in physics, when you think of velocity, maybe negative is going in the opposite direction. This is doing exactly the same thing. The minus out front is telling you you're going backwards. You're now going in the opposite direction to what I thought you might have been going on. Okay, let's do another one. Zero width interval. So that means a to a of f of x dx. Now, if I was in person, I would call on somebody in class to tell me what the answer is going to be, but unfortunately, there's no one around. It's just me, so I'm going to call on myself to answer this, and I'm going to explain it. The answer here is 0. Now, why is this thing 0? Well, let's think about it again, right? Again, all of the properties are coming from delta x. So if you think of this in terms of the Riemann sum, so finitely many subintervals, you're going from A to A. What is your delta x value? A minus A divided by n. Nothing special. 0 on the top, n on the bottom. Boom, delta x is 0. Then that means that your Riemann sum, so let's go back to the picture here, or to the equation. This guy right here on the left is 0. And so as you pass to the limit is still 0. And so that means that the right-hand side has to be 0. Nothing fancy, nothing special, just a property of the delta x choice, just like number 1. Okay. How about constant multiples? So I have k times the function f of x, and I want to find the definite integral over the interval a to b. So I ask myself, what should this be? Well, let's think about this, okay? So again, let's go back, think about this in terms of my Riemann sum. What happens? Maybe I shouldn't use k here. Maybe that's not a great choice. Let's see. Well, we're going to use k because we don't have the Riemann sum. I apologize if this is confusing to everyone. K is a constant, so k is a real number here. Okay. Well, what happens? Okay, so the delta x is still the same. You're still going from A to B, so nothing changed there with the Riemann sum. But what happens with the height of each of those rectangles? When you were originally going up to f of x, now you're going up to k times f of x. And you're doing that for every single rectangle. So if a rectangle was height 1 before, now it's height k. And you stretched every single rectangle up k, which means that you just multiplied the area by k. You just stretched it in one direction by k. And so that means that you can pull out that constant and you can just multiply it by the area, right? So this is just an area stretching property, right? If I have a rectangle, or just some shape, it could be a rectangle with height 1 and length 1, so it's a square. If I double one of the sides, the area becomes doubled as well. If I triple one of the sides, then the area becomes tripled as well. You're just stretching in one direction, and that's all that's telling you. And that's a beautiful property too, right? Because that tells me I don't need to recompute a bunch of stuff. That tells me all I need to know is the integral of f of x. And then if I want to know k times f of x, I just multiply that original area by k. Boom, life is good. Okay, sums and differences. So this is probably somewhat predictable as well, but if I have the integral of f of x plus or minus, doesn't really matter, g of x over the interval AB. Well, what's happening here? Well, what's happening here, again, if you think of this in terms of Riemann sums, you can prove everything that I'm showing you here today if you just use the Riemann sum. Well, what is the height of each of those rectangles? It was the height at f of x plus the height at g of x, or minus, depending on which one you're going to use. So if you go back to your formula here, you're going to have f of ck plus g of ck. You can distribute the big sigma, the big sum, the k equal to 1 to n, over each one of those, that the f terms and the g terms. And then you just arrive at the usual Riemann sums for f and g independently. So this tells you that the integral of f of x plus or minus g of x is the same as the integral of f of x plus or minus the integral of g of x. Again, life is good, right? This is a reduction in complexity of things that I need to compute, because really I just need to know the integrals of f and g independently in order to get the integral of f plus g or f minus g. And you can combine that with the constant multiple rule to get multiples of these things as well. Okay, let me show you another cool one. Additivity. Okay, so this one says that if I want to take an integral from a to b, and I add it to an integral from b to c, then this is the same as going all the way from a to c. Okay, so this one sort of intuitively makes sense, right? Because if you think of, building these intervals, right? So if this, let's make them uneven just to make it slightly more exciting. But here's A, here's B, and here's C. If you're going to calculate the integral on up to here, and you're going to calculate the integral up to here, well, if you think of how these Riemann sums are created, it's just stretched over entire intervals. And so that would make sense because A to C forms an interval. B is just a sort of wayward stop. You told yourself, okay, let me get all the way to B first, and then I'll stop and take a break and set up camp. And then in the morning, we'll go from B to C. But that's the whole principle here, right? And you can, again, I'm sort of being fast and loose with this, but that's okay. It's better that you understand the property and how to use it than how to demonstrate it. But again, you want to demonstrate it, go back to the Riemann sum, write it down. Just that's as simple as it is. You can prove all of these with pen and paper in a very, very straightforward way. Okay, so let me give you another one, max-min property. It's the max-min property that I sort of played with a little bit with that, that function that can't be integrated on the previous page here. And basically the max-min property says the minimum value, the minimum value of f times the length of the interval is less than or equal to the definite integral, which is less than or equal to the maximum value of f times the length of the interval. Okay, let me, this one is maybe not as obvious, but let me show it to you in terms of areas, because then I think everybody's gonna agree with me that it is quite obvious. Okay, let's imagine I've got a function. Here's my function, Let's say here's A. Let's say here's B. And in terms, let's shade it in. Here's the area that I want to calculate, right? So that area is this definite integral, right? Just by what we know about Riemann sums. And we'll come back to this. We'll formalize it. We'll make it more precise in a moment. But here's the minimum right here. And here's the maximum right here. Okay, so think about this constant function. That constant function is y is equal to the minimum of f. And this constant function, it's not perfect, but this is y is equal to the maximum of f. Now, what is the area underneath y is equal to the minimum of f? Well, that would be, so maybe I'll put this in brackets or something. The area is equal to the minimum of f times the length of the interval. Why? Well, it's just a rectangle, right? Look at it right here. The height is the minimum of f. That's how high you're going up. And the length is the length of the interval. So then the same thing happens for the maximum of f. So area is equal to the max of f times the length of the interval. Again, it's just a rectangle. But you can very easily see that you're overestimating using the maximum and you're underestimating using the minimum. So that gives you exactly this property that the minimum of f times the length of the interval is less than or equal to the area underneath f, or the definite integral, and that is no more than the maximum times the length of the interval. That's a sort of geometric way of proving this. And finally, this can become slightly more abstract. And you can think of this not in terms of mins and maxes anymore. You can think of this in terms of functions. So you can say, if f of x is less than or equal to g of x on the interval, then the definite integral of f of x is no bigger than the definite integral of g of x. Okay, again, let's just draw a picture, right? Sometimes a picture is worth 1,000 words, and in this case, it certainly is. So let me draw you two functions. Here, oh, sorry. Here is f of x, and let's make g of x slightly more exciting. It's not supposed to be that shaky. That's just slipping on my screen. But here, let's say this is A. Let's say this is B. Well, you can clearly see that the area formed by f of x has to be less than the area formed by g of x, right? You can see it from the picture because g is above it, right? So there's all of this area in here that's being counted towards g that is not being counted towards f. And there's a nice little corollary of this, a consequence of this, that if f of x is bigger than or equal to 0, which has been the case with all of the pictures that I've drawn so far on this interval, then this integral has to be positive. So these are some nice properties. And this last property, this last property leads me to something that I've kind of been sweeping under the rug, right? So I think it's appropriate for me to address this. In my pictures, I've been talking about how this is area under the curve. But it's not really area under the curve unless I actually satisfy this condition right here, right? Because what about this curve? Let me give you a weird looking, or not even weird looking, but just a curve where, oh, sorry, I keep leaving this thing on. Okay, let's start from the beginning. So what I'm going to draw for you is a curve that goes below 0. And you ask yourself, what is the area, or what is the definite integral representing in this case? So let's say this is going to be A right here. This will be B right here. So then, what's happening? Well, okay, this area, where this thing is positive, the area sort of makes sense, right? The question is, what happens in the middle? There's nothing above the axis to count as area. Well, the way this works, if you think about the Riemann sums. Everything is built from the Riemann sums. Anytime you're worried or you're confused about integrals, think back to Riemann sums. Think of little rectangles, and it's there's a sort of Zen nature to that. But let's imagine we have little rectangles in here, right? Because that's what the Riemann sum is telling us. It's saying you have to go down to the function now. You can't go up to the function because f is negative. So what's happening? Well, it's calculating, if I can color over what I just drew, it's calculating this area now, this below the x-axis area. And it's going to tabulate this as negative. Why? Because the f is negative, that's coming through in the sum. So these definite integrals, they give you an area bounded between your curve and the x-axis, and this area comes in quotations. This area is signed. If you are above the x-axis, that area is positive. If you are below the x-axis, that area is negative. So down here, you have a negative contribution. I'm going to put area in scare quotes here because it's sort of a weird way to think about area, right? It's very abstract, but it makes more sense when you think about this in the context of how we interpret some physics, right? We think of velocity as being positive or negative depending on which direction you're going. Well, this has the same sort of idea. If your direction here, if you're going up from the x-axis, the area is positive. If you're going down from the x-axis, your area is negative. And so this means that you can sort of cancel out area, right? Because there's time spent below the x-axis. Okay, so that was a bit of a rant. Let me show you, let's use these rules. Let me give you some examples. Okay, so let's suppose we did some work and we calculated the integral of f from -1 to 1, and we found that that's equal to 5. We found that from 1 to 4 of f of x, this is equal to -2. And there's another function from -1 to 1, h of x, that we also calculated, and we found that that's equal to 7. Right, so we did this using Riemann sums. We did it the old-fashioned way, the same way we did in the previous video. But now here's the beauty of a lot of the properties, right? Okay, so then, well, first of all, the integral from 4 to 1 of f of x. Well, this is going to be property 1. So let's put a little note here. I'm going to put a 1 over top to denote that that's property 1 doing this for me. This is the minus of the integral from 1 to 4 of f of x dx, which tells me this sort of, again, generalized area is equal to 2, right? It's minus 2. Okay, let's do another one. let's ask ourselves about the integral from -1 to 1 of 2f of x plus 3h of x. I'm going to write this out carefully. So first, I'm going to use, let me double check my properties, the sum property here first. Sorry, we're going to go back. So property number 4 says I can distribute this over the sums. So let's do that first. Property 4, distributing over the sums, -1 to 1, 2f of x dx plus the integral from -1 to 1, 3h of x dx. Then let's use property number 3 to pull out those constants. So I get 2 times the integral from -1 to 1, f of x dx, plus 3 times the integral from -1 to 1 of h of x dx. Now, I know what the integral of f of x and the integral of h of x are in this case. So I get 2 times 5 plus 3 times 7. So this gives me a nice 31. All right, one more to really drive it home. Let's ask ourselves, what is the integral from -1 to 4 of f of x dx? Well, let's go back to look at the properties, right? Because this one is not given on the list. So let's take a look. Which one of these do we think we want to use, right? So the order of integration, no, that's not going to help us. Zero within width interval, no. Constant multiple, no. Sums and differences, no. Additivity, that's kind of interesting, right? Because we are going from a equal to -1 to c equal to 4. But the integrals that we're given, they have a breakup point in the middle at 1. They're a little way station. So let's use additivity. So here we go. Let's denote what property we're using. And let's use the integral from -1 to 1 of f of x dx plus the integral from 1 to 4 of f of x dx, which gives me, let's take a look, 5 for the first one plus -2, which tells me the area, or the generalized area, if you want it, I think you should think of it that way, is equal to +3. Okay, let's do another example. So let me do another page here. I want you to not calculate an integral, because this is going to be an ugly one, even if you try and use the Riemann sums. But I want you to bound an integral, right? So I'm gonna say show that the integral from 0 to 1 of the square root of 1 plus cos of x, sorry for the zoom in, dx is less than or equal to 2. I remember hearing this quote one time where somebody said, the worst thing that mathematicians give the impression of, I'm paraphrasing, but the mathematicians give the impression that all of math is about equality, right? This is equal to this, is equal to this, equal to this. But that's not true, right? Like 99% of math is actually inequalities, because we can't solve things exactly. So the best that we can do is say, it can't be bigger than this, or it can't be smaller than this. And I can attest to that, right? In my own work, it's constantly inequalities. I hardly ever use equalities. Okay, so that's enough of my silly little rant. But how are we going to actually do this? Well, we can use that min-max property, right? So we're going to, oh, sorry, let's denote, let's use, I believe it's 6. Maybe I should just double check that so that I don't have anything. Yeah, it's number 6. Okay, so how are we going to use 6 to bound this? Well, what do we know about cosine? We know cos is between -1 and 1. Good. Then if we add 1 to all three terms here, we get that 1 plus cos is between 0 and 2. Then, because everything is positive, we can take the square root and the inequalities are preserved. So I get the square root of 0. So that's going to be 0. I'm not going to put a square root over it. It's just a waste of writing. Then the function that I care about. And then the square root of 2 again. So the maximum value of this thing is going to be the square root of 2. Furthermore, maybe we should write a little note. This is actually attained. So this is the strict maximum. Oh, sorry, that shouldn't be less than or equal anymore, right? So not like this isn't a bad bound. This is as good as it's going to get because this is the actual biggest value the function can take on. So the integral from 0 to 1 of this function, well, by property 6 is equal to the square root of 2 times the length of the interval, 1 minus 0, which is just 1, which is the square root of 2. So this is good, right? This provides us with a method of understanding, you know, it's not perfect, right? It didn't tell us a whole lot, but it told us that this integral can't be bigger than the square root of 2. That's a lot better than where we started, right? Because where we started, we said, I don't know, it could be anything between minus infinity and infinity. I have no idea. And in fact, we can also put a lower bound on this because we know that the function is bounded below by 0. So we can actually, you know, sort of wedge this Riemann sum, this definite integral, in between 0 and square root of 2. It's not perfect, but it's much better than what we started with. Okay, so let's play with this a little bit more. Let's keep doing some examples. I really want to make this concrete, and let me give you another nice example here. So we're going to move away from the properties, or we're going to sort of use them implicitly behind the scenes, but we're going to compute the integral from 0 to b of x dx on 0 to b, where b is greater than 0. I guess you know what? I don't need to write on 0 to b because that's sort of redundant, right? That information is encoded in this expression. The interval is from 0 to b. That's written on there, so I'm being redundant, right? Okay, let me draw this thing first. Okay, my function is a straight line. It's x. So that means I've got that. I'm going to come up to, say, b here. This is my b. Oh, auto-corrected me to 0. So there's my b. And we have this abstract notion of the area underneath the curve. So we know that that's exactly what that definite integral is describing, right? So we can calculate this in two ways. Let's do it with the Riemann sum method to start with, and then we will we'll move on from there. Then we'll just do it like the old school way we probably did in elementary school. We can actually just calculate the area of this triangle that this thing is forming. So first, with Riemann sums, right? We have to torture ourselves a little bit just to get used to this. Okay, so clearly this thing is starting at 0. And so then the x sub k's are going to be k times b over n. Again, This is a continuous function. We can use that theorem. It doesn't matter how we want to set this thing up. So we can use the left endpoints or the right endpoints. We can use the midpoints. It doesn't really matter, right? Your CKs can be chosen in any way that you want. I'm going to choose the CKs to be the right endpoints of each interval, right? So I'm going to set CK is equal to, or sorry, the left, yeah, the right endpoints, because I'm going to start counting k equal to 1 all the way up to n, sorry. And this will be kb over n as well. So if we want to draw this in here, make it look nice. So let's just, I'll put in a couple of them just so that we're all on the same page. And this is b over n, this is 2b over n, this is 3b over n. And same thing, right? Because the curve is just x, this is 2b over n, and this is 3b over n, and so on and so forth. And delta x is equal to b over n. So let's calculate out our sums in terms of just general n. So this is f of ck times delta x. This becomes the sum of kb over n multiplied by 1 over n. Again, from the example that we saw at the end of the previous lecture, the only thing in here that's changing over the sum is the k's. So let me take the b's and the n's out. This becomes b over n squared. And then the sum of the first n integers. This is usually a formula that a lot of people have seen. I'm not 100% sure who has and who hasn't, but this is a very, very famous formula. And it's given by n times n minus, or sorry, plus 1. It's so famous that I forgot it, right? Okay, so then we can distribute this out. We can make it look a little prettier. And this gives me b over 2. Oh, I made a mistake, right? This should be b over n. I'm sorry, everybody. Delta x is b over n. I wrote it as 1 over n. I apologize to anybody who's following along at home. So this is b squared over 2 times 1 plus 1 over n. Okay, that's good, right? Now I have a general formula in terms of the n's to figure out what exactly the Riemann sum is, right? So n is equal to 1,000. I just put n equal to 1,000 in that thing. Life is good. So let's start a new page and let's take the limit. So the limit as n goes to infinity of the sum from k equal 1 to n, f of ck delta x is equal to the limit as n goes to infinity of, what was that? That was b squared over 2, 1 plus 1 over n. The only piece of this that's changing with n is the 1 over n term. And as n gets big, 1 over n gets small. And this guy, we can say, see you later too. This leaves me with b squared over 2. Wow, that was a lot of work. But this tells me, this is exactly the integral, by definition, the integral of x dx from 0 to b. Okay, that might have been a little overkill though, right? Because we understand that this is calculating an area. This is the fundamental principle of these definite integrals. So let's go back and let's look at the picture for a second. This thing has base b, it has height b. I can calculate areas of triangles, right? It's 1/2 base times height. So using the area of a triangle, well, this tells me the integral from 0 to b of x dx is equal to 1/2 base times height, which is b squared over 2, which is exactly what we got with Riemann sums, which is good, right? Because that means that we have a consistent definition. If it doesn't work on the examples that we know it'll work on, there's no point in making that definition because it's just impossible, right? It's just not consistent with how we think about area. So if this is going to be an abstract notion of area, it's got to at least account for the area that we understand and can calculate. Okay, so let me finish up this lecture by just coming back to something that we introduced in the previous lecture, and that is average values of functions. Okay, so let me scroll up here. So average value of a continuous function. So I gave, in the previous video, I gave an explanation of this. There was a little fast and loose, right? I said it's, you can think of it like a weighted sum, and you take these rectangles, you divide it by the length of the interval. Well, now we can do it properly, right? Because we can say, what is the exact average value of a function over an interval, right? So let's say we're given y equal to f of x on an interval AB, then the average of f of x. So this has, a lot of people use different notations for this. Some people will write AVG of f. Sometimes people write like AVG sub AB. You know, there's like all kinds of really ugly notations for this. Sometimes people write f bar, like a bar over top. I'm going to write AVG of f. This is 1 over the length of the interval. Remember, that's the sort of the sum of the weights. You should think of it that way. And then a to b f of x dx. So it's just the definite integral divided by the length of the interval. That's all that it is, right? So this just tells you exactly how to calculate the average value of a function over some interval. So let's ask ourselves, let's do an example on this. Let's do a relatively difficult example. Let's find the average value of f of x equal to the square root of 4 minus x squared on -2 to 2. So why did I say this is a difficult example, right? How do I know something is a difficult and something is an easy example? Well, that function's pretty ugly, right? So I dare you, and write to me if you end up doing it this way and you get the right answer. Do this with Riemann sums. It's going to be ugly and it's going to be hairy, right? Because you're going to have to add up all of these square roots, which I don't know, maybe there's formulas for, but I certainly don't have them memorized. But okay, let's start with a picture, right? This is half of a circle. This is the upper half of a circle. So bear with me. Oh, this screen is slippery in my defense, okay? So here is my area underneath. This is -2, this is 2. So this is abstractly, this is my abstract art, but it's supposed to be a perfect semicircle. And it's above 0, so it should be interpreted as an area. So then I don't actually have to do a Riemann sum, right? Again, from the previous example, I know, or I expect, and we should believe that the classical notion of area of something, things that we can calculate, squares, circles, etc., should line up with whatever's being formed between the x-axis and the curve. So I don't have to do any work here, right? Or I have to do very little work, because this tells me that this definite integral is just equal to area of a semicircle, which is 1/2 pi r squared, right? The 1/2 is the semi part. That's the upper half of the circle. Pi r squared is just the area of a circle. So this gives me 1/2 pi, and the radius of this circle, well, this, maybe I should put this in a different color. This 4 here, this is the radius squared. So that means that the radius is equal to 2. So this gives me a area here. The green portion has area 2 pi. So that tells me that the average of F is equal to 1 divided by B minus A times the definite integral which is going to be 1/4 times 2 pi, which is equal to pi/2. I love calculating averages of functions. Why? Typically, it's a question that gets asked on tests a lot, and it's really no more difficult than the other, getting asked to calculate a definite integral, right? Because it's really just calculating a definite integral and then just scaling it, 1 divided by the length of the interval. So the reason I love it is because it's usually free marks on a test, right? It's a question that has to be asked because you have to understand it, but it's also, something that's relatively easy. It's a fairly trivial extension of what we've already been working on. Okay, thank you, and I'll see you next lecture.